Greetings, fluid mechanics enthusiasts. Here is Leonardo. How you doing? Well, in this video I'd like to cover a topic which is how the airplanes fly. There's a lot of videos on YouTube. While they try to clarify some concepts, they make often some conceptual mistakes, and people who aren't very familiar with fluid mechanics, they don't have a real practical overview of how the equations underlying, the physics underlying this phenomena apply in this case. Okay, fly is a very complex phenomena. You can really explain in a simple way that without making some oversimplifications and often some conceptual mistakes, as I said earlier. But we can look at the phenomenon of flying, simplify it to what happens in the wing. Of course, when the airplane is flying, there is a relative flow of air on this plane, and this flow interacts with all parts of the airplane, generating lift. Okay, so the airplane is in the whole, it helps generates lift, but we can narrow it to what happens on the wing, as it is the primary part of plane that contributes to generating lift. So let's look at what happens on a wing. So here we have a typical airfoil, which is a very known airfoil, which is the NACA 0012, which is a typical profile of wing utilized in airplanes. So what happens in airflow? Let's use Newton's force diagrams. Here we have lift, force which tends to pull up the airfoil. Here we have its weight. Here we have drag, and here we have thrust. Okay, so in order to an airplane to maintain its height, all these forces need to be balanced. But if it wants to obtain height, in the case of an airlift, of a lift-off, its force of lift, of course, it must be greater than its weight. Okay, these two forces here, drag and lift, they both depend on the airflow around the airfoil. Here, of course, we are talking about flight at subsonic levels, because flight at the speed of sound and supersonic flight and hypersonic flight, the mechanism behind the airflow, it's different. Okay, so these two forces here, lift and drag, they depend on the characteristics of the flow. So typically the lift force has this expression here. It's 1/2 the density of the air, lift coefficient, the flow velocity, mean velocity, and area, projected area, horizontal area on which the flow is occurring. So how do we obtain this coefficient here? How lift is generated? That is the main question behind flying. We have our airfoil and we want to generate lift. So assume that the air is flowing. We don't have any angle here. It will occur something like this. We have here the streamlines of the flow, and they are symmetrical on the upper part and on the lower part of the airfoil. Okay, so here it's air flowing from, let's say, point A to point B, right? So when air flows from A to B, its field is disturbed by the presence of the airfoil. So it generates the separation of the flow due to its presence. So when the air encounters the airfoil, it generates a field, a pressure field along the airfoil. Okay, remember that when there occurs fluid flow, we have two main forces that the fluid exerts on a certain body. There can be others, but the two main forces here are pressure and viscosity, stress. In this case, shear stress. And pressure, which is a compressive force. So on this case, there will be no lift generated because as the flow is symmetric here and the airfoil orientation relative to the flow, which is here, the angle of attack, we usually denote the angle of attack as alpha. Here it will be equal to 0. So the forces on the upper part and then the lower part, they, let's say, are equivalent to one another. They equal one another. In the case where there is a certain angle of attack, on this case it's higher than 0, so we have lift. What will happen on this case? Here we have our streamlines. So the airfoil, the disturbance of the airfoil on the flow modifies the streamlines distribution. So it will induce a different velocity here on the, let's take here this section here from A to B, okay? So the velocity here on the same distance from a certain point here and here on the airfoil, it will have an asymmetric distribution, okay? So velocity here, let's take an equidistance point from here to the lower part and from the upper part, it will have a different value, okay? So that will generate a different distribution of pressure and of shear stress, which will in turn generate lift. The lift force depends on the lift coefficient, right? The lift coefficient in turn is a function of the shape of the airfoil, the geometry of the airfoil, function of geometry. From it will have a different value for a different angle of attack from the speed of the airflow, from the mean speed of the airflow, among other variables. But on this case, its main variables are the geometry and the angle of attack. So that is what will generate lift and causes a different distribution of pressure and shear stress along the surface of the airfoil. So here we have a typical pressure distribution for flow over an airfoil. Here it is not a symmetrical airfoil, but nonetheless is the same mechanism for a symmetrical airfoil. And under the airfoil here we can see that the velocity is pointing on the direction of the airfoil. So it's a compressive force which will pulse the airfoil up, and on the upper part of the airfoil we have a positive pressure here which will also pull the airfoil up. Of course, we also have the shear stress due to the air viscosity, but for this type of flow, the pressure force is much greater than the shear stress, and the shear stress due to the fluid viscosity, the air viscosity, will primarily induce drag on the airfoil. Okay, here we have a numerical simulation of the flow over a symmetrical airfoil. On the upper figure we can see the vorticity, the formation of vortex along the airfoil, and on the bottom figure we have the component of velocity in the x direction, which will be along this direction here. So what is been varied along this simulation is the angle of attack of the airfoil, and here you can see the two components of the force along the airfoil. On the upper part of the airfoil and on the bottom of the airfoil. So that's why we have two lines here and here on these two graphics. So here it will be the coordinate along the x direction of the airfoil relative to the chord, which will be this distance here. So here we have the pressure contribution of the force along the airfoil, and here the friction due to the viscosity shear stress. And you can see how it is varied when the angle of attack of the airfoil is varied. When the angle of attack is higher than a certain value, you can see that when it's increasing, the vortex formation increases, so there's more turbulence, and that's why you see these fluctuations, these higher fluctuations on the friction coefficient of the airfoil, because as the vortex when we have turbulence are the primary generators of friction on this case. Also, because velocity and pressure are coupled, you have higher fluctuations on the pressure coefficients, primarily on the on the final edge of the airfoil, okay, at the end of the airfoil. So when its angle of attack is close to zero, you have little turbulence. That's why you have the lower value for the drag for the airfoil. And here you can see how the streamlines of the flow, they are modified when the angle of attack of the airfoil changes. Here they stay more closely together for a higher angle of attack, and if the angle of attack is zero, these streamlines on the upper part and on the lower part of the airfoil, they tend to be symmetrical. Okay, here you can see the streamlines which correspond to the vortex formation. Here you have the vortices, as you can see here, and with no angle of attack you have little turbulence just on the final part of the airfoil. It is frequently said that what generates lift on an airfoil is the velocity, while some others say that what generates lift is actually the pressure. Both are wrong and both are equally right. Why is that? Well, both velocity and pressure generates lift. Let me explain. Well, in fluid mechanics and fluid dynamics, pressure and velocity for subsonic flow speeds, they are coupled, okay, by the Navier-Stokes equations. The Navier-Stokes equations along with the continuity equation, which are both equations of conservation. Navier-Stokes equation is a conservation of momentum. It's equivalent to Newton's second law. And the continuity equation is an equation of conservation of mass. Both these equations, when coupled, they couple pressure to velocity and velocity to pressure. So when you're talking about velocities, you're also talking about pressure. And when you're talking about pressure, you're talking also about velocity. So you can really separate decoupled pressure from velocity. You can treat them separately. Okay. So both velocity and pressure generate lift. When you try to modify the pressure field along a wing, an airfoil in this case, or when you try to modify the velocity field, you will alter the other. Okay, so you can't modify the pressure without modifying velocity and vice versa. So what generates lift are both velocity and pressure. Okay, when we are dealing with increasing the lift of a certain airfoil we are designing, we'll try to obtain the most optimal geometry and of course the most light material that is also have some resistance to the stresses that we will be subjected to. And we will look at how these airfoils behave at different angles of attack. So typically what we obtain is as follows. Here we have the lift coefficient. Each airfoil has a graph of this type. Typically the lift increases linearly with increasing the angle of attack, but at a certain critical angle of attack we obtain what is called the stall. So if we increase the angle of attack further, we will lose lift. Okay. There are certain types of airfoil which are asymmetrical. Okay. So these types of airfoils, we will have a lift different than 0 for the angle of attack equals 0. The lift force on an airplane will depend on the density of air, the lift coefficient, the velocity of the airflow along the airfoil, and the horizontal area projected of the airfoil. Okay, so one way to increase lift on the airfoil for this force to be greater than weight, we can increase the airfoil along the airfoil. So the force will depend on the square of the velocity. That's why we need turbines and propellers on our airplane to increase the flow velocity and increase lift. So we can't modify the density of the air. It's not a controllable variable. We can modify the area, the horizontal projected area of the airfoil in order to obtain lift. But as we increase the area of the airfoil, we also increase its weight. So we have to find an equilibrium between the projected area of the airfoil, which will generate more lift, and along with its size, because we will also increase the weight of our airfoil and thus our wing. So we have to focus primarily on the velocity of the air through the propellers provided by the propellers and turbines, and the geometry of our airfoil, which is the main variable that will modify our lift coefficients by modifying the pressure fields and shear stress fields along the airfoil. So I hope you enjoyed this video. Don't forget to like, to subscribe and comment, and share this video with others. See you next time. Bye.